Hello. Hopefully by the end of this video we'll get to a point where we've set up the soft stretchy IK on the arm joints. But before we move on, I want to go over why exactly we used the expression or the equation that we did for the wrist locator. So I always think it's important to understand the theory and rather than just inputting values. So here is what we did in an expression, and here it is actually written out as an equation. Now let's assume over here that all of our variables have been set up and that our control distance, which is the distance between the upper arm locator and the arm control distance locator, is greater than the chain length minus the soft p attribute. So in other words, we're in the body here. Obviously if soft p is equal to 0, then it just returns the chain length. So if we say soft p is greater than 0, then we're using this equation here. And you can see what we get is the chain length minus some other part here. Now over here I've called it soft pause because I actually used this in my 3ds Max video series as well, but soft distance and soft pause is the same thing. So let's put in numbers here to complete the entire equation. So let's assume the control distance is 7 and the soft p attribute is 0.2. Then you can see what we get is 7 minus this part here. And now you can see that we're beginning to get the wrist locator to lag behind the arm control. So if we just go into Maya and actually put those values in. Now I froze the transforms in this control, so if I put it forward 1 in x, that'll be 7 units in world space. And now if I put in soft p value of 0.2, you can see the wrist locator just moved back slightly. And the translate x value is 6.926, which is exactly what happened, exactly what we had in the other Word document. Now something which is interesting as well is as the control distance increases a lot, then the bottom section of this fraction becomes large, and that when you multiply another number by this fraction, it reduces the effect of this. So eventually what's going to happen is only the chain length is going to be returned, and that's why the wrist locator never goes past 7, because the length of the chain is 7. So you can see if I increase this, I'll put it all the way to 1 just so it's very easy to see. So we have this effect here, and as we come out, the wrist locator begins to slow down until it reaches a value. It reaches 7. And you can see that's as close as we can really hope for to get to 7. Okay, so hopefully that explains why we use that equation. So now we'll get started with doing some of the other stuff. And first of all, what I want to do is make sure that this is scale independent. So in other words, it correctly interacts with the scaling. So if we select our root control and scale that, you can see that actually it's not, because as we reduce this down, the wrist locator isn't sticking to our arm control like we want it to. The reason for that is because the measure distance tool measures the distance in world space, whereas what we're doing is we're inputting a value into the wrist locator in parent space, and its parent is being scaled here. So what we need to do is find a way to basically negate the scale in our node graph. So if I just place all these back to 1, and the way we do that is quite simple. What we need to do is just take our root and scale x, for example, and redefine the control distance to be the control distance times 1 divided by the root scale. So before I do that, what I'll do is I'll just go to my connection editor, and I'll go to scale x, and I'll just connect the scale x to scale y and z. So now I can't non-uniformly scale this object. So it's always going to scale uniformly. And we can just lock and hide those as well. Okay. So here's the node graph again. And what we want to do is just bring in our root. And you can see now we have connection back to itself, but that's fine. And we want to create a multiply divide node. And it's going to be 1 divided by the scale x. Another multiply divide node. Multiply. And now what we're going to do is multiply the distance here into here. Okay, and that's exactly now this. So we've got the 1 divided by the root, what I'm calling the root scale, and then we've got the control distance multiplied 1 by divided by the root scale. So now what we have to do is actually replace all of the connections from the control distance into the other nodes with this. So I'll just say output x and place that there. And let's just take that down, so that's the, oh, it's not there. So it's, we can read it from here, so it's the color if false and the first term. So there's the first term. And there we go. So now when I select this and scale it, now it all works as we expect. Okay. Now what I want to do is create a point constraint between the wrist locator and the arm control, and that point constraint is going to be created on the soft blend locator. So let's just navigate. There's the soft blend locator there. There's the upper arm. Sorry, it's the wrist locator we need, I beg your pardon. So wrist locator, arm control, and then soft blend locator, constrain, point constrain. And now if I move this out, you can see here's the soft blend locator. So this is going to allow us to blend between the non-stretchy soft IK and the stretchy soft IK. And we're going to control it with the stretch parameter here. So what I'm going to do is create a set driven key connection which will allow us to blend between them. So I'll just go to animate, set driven key, set, and I'll load this as the driver, and we want the stretch value, and I'll select this. I'll just select the point constraint, load that as the driven, and we want the two weights here. So when the arm control stretch is equal to 0, we want no stretching, so that's going to be it back here at the wrist. So in other words, we want the arm control weight to be 0, and we can key that. Oh, I need to select the driver. Key that. But when stretch is equal to 1, we want the opposite thing. So this has to be 0, and this has to be 1. And we can come back and key that now. So now if we come up to our stretch, you can see we can blend between the two. Like that. Okay. If we turn stretch to 0, everything seems to be working fine. One thing you'll notice is if you have a look at the upper arm joint here, as I pull the control away, see how it sort of snaps there? As we get to a certain point, it sort of just snaps down. Hopefully you can see that. The reason for that is because of the default value of the tolerance in the ikRPsolver. Now it's set to 0 in the user interface, but if we say get attr ikRPsolver.tolerance, you can see it's not actually quite 0. It's a very small number, but it's not quite 0. So what we're going to do is actually we're going to reduce this. So we're going to say set attr ikRPsolver.tolerance, and we're going to set it to 007. So we're going to reduce it by 2 more decimal points essentially, and evaluate that. And now that should get rid of that sort of snapping effect we were seeing before. So now it just goes down smoothly. Okay. So now this is the section that we're working on now. So we need to create this in a node graph. So again, there's going to be a lot of multiply divide nodes. So this is our wrist locator setup now. So that's finished with. But I did create a bookmark for that just in case I needed to get back to it. But what I'll do now is just select the upper arm and the wrist and just show those input and output connections. We don't need these two nodes here, so we can just remove them from the node graph. I'll start just by creating a multiply divide node, and you can see this expression was applied to the lower arm, and the bone length or the joint length of the lower arm is 3 because it's got a translation value of 3 in the parent space. So we're going to need to do this sort of twice because the wrist will have a bone length of 4. But we'll work on the upper arm to start off with. So we'll just say divide, bone length of 3, chain length of 7. And I'm actually going to rename this because we'll need some of these 3 divided by 7 and 4 divided by 7 later on. So I'm going to call this divide 3 by 7. So that's us created this section. We need to create the soft len as well, so that's the soft distance shape multiplied by our 1 divided by root scale to sort of cancel out the scaling. So let's get the soft distance. We'll enable shapes. Take that in. We'll get our root. We'll take that in. Multiply, divide. One divided by scale x. Another multiply, divide, that's set to multiply, that's fine. Distance in output x. Okay, so that's the soft len created. So now we need another multiply, divide node to multiply these two things together. So that's us created this section now. So we have the soft distance there being multiplied by the scale x, that's 1 divided by scale x, and then we're multiplying them together. And up here is our 3 divided by 7. So now we need the arm control. Because now what we need to do is get our stretch p parameter. And that's going to mean that we'll need another multiply, divide node. And finally, we're going to add our bone length. So now we'll need a plus minus average. And I'll just create it, then remove it, and then define it here. So the bone length again is 3. And now we can place that into the lower arm translation x. So basically the way this works is we're creating a small multiplier value to add to the original bone length, and that's what's causing the stretching. So the soft length is equal to the distance between the wrist locator. If we go up here, so the wrist locator and the soft blend locator. And the soft blend locator is that one that we just applied the point constraint to. And then what we're doing is we're multiplying it by a fraction so that our joint is going to move proportionately. And then we have our stretch p value so we can turn it on and off. So this is a value between 1 and 0. So if it's 1, we're going to get this full term here. If it's 0, then this is just going to leave us with the bone length, which is how we get our non-stretchy soft IK. Okay, so now we have to do a similar thing for the wrist as well. We don't need to redefine anything here. This is fine. This is the soft len. But we do need to create a 4 divided by 3 node. Divide 4 divided by 7, I beg your pardon. And I'll call it that. Divide 4 by 7. And then we'll multiply them together using another node. So that's us done this section here. Now we just need to incorporate the stretch parameter, I beg your pardon. So I'll take this and put it into the first input. We've got our arm control here, which has our stretch on it. Input 2. And now if we just duplicate this plus minus average, you can see it already has 2 channels available for us. So on the second one, because bone length to be 4 this time, so now we've got all this, and now we're doing this. So the bone length again is 4. We changed that over here. We did it 4 divided by 7. So now we just need to sum these two things together. So that's that created there. And now we'll put this into the translation. X. So at the moment we don't have any stretching on. So we take this down, and there's the non-stretchy soft IK. Let's reduce the soft value because it's too high. Put the stretch to 1, and let's begin to move this out. And there you can see the soft stretchy IK. And again, we can blend between these two. So there's your non-stretchy soft IK. Okay, in the next video I'll go over how to set up IK pinning.